The next scheduling policy is a round robin. Round robin is what? It's basically it's a turnover. It's a turnover kind of a scheduling strategy. It doesn't really care about the length of the each process, but in a very short time, it give a chance to each process to execute. And when the time expire, then it just schedule the next one without really considering any priority over the different processes. So round robin scheduling policy is to provide better, good responsive time, good performance in terms of the responsive time. So what it means by responsive time? Time for a process to be launched or job to be alive, and to the first time it get executed or first time it make a response. But defining the time, the first moment of making a response is really tricky to define because it depends a lot of the specific program behavior. So usually it is measured by the first time it gets scheduled after it's put to the ready queue. So this is important for interactive program, as I told you before, for like a web browser. I mean, yeah, optimizing turnaround time doesn't really mean much, but it should be a responsive time, the optimization object for a web browser like Bing, because it the genuine purpose of it is to make a smooth interaction with the users. 사람이랑 잘 해야 되죠. 사람이 여러분 컴퓨터 프로그램 딱 눌리고 나서 프로그램 느리네라고 느끼기까지 시간이 얼마쯤 걸린다고 들었어요? 혹시 그 이야기 들어봤어요? 그 실제 서베이가 있는데 이거 안드로이드 앱에서 서베이인데 안드로이드 앱에서 여러분이 앱을 딱 눌리고 크기까지 3초가 넘어가면은 그 앱을 지울 확률이 드라마틱하게 높아집니다. 예. 예, 실제예요. 그래서 이제 무조건 일단 로그인 안 해도 서비스부터 제공해주게 이렇게 많이 돼 있는 이유가 그래요. 사람이 딱 켰는데 1, 2, 3 이러면은 여러분이 못 견뎌요. 현기증 나 이런단 말이야. 나도 현기증 나요. Response time is somewhat more really important. So round robin is aimed for achieving reliably good responsive time. So simply RR, run up drop for a time slice. Time slice usually was often coded as a time quantum. It usually means very short term of a time, and quickly switch to the next one in a ready queue without considering anything. Just it provide a fair chance to the whole processes to make an execution for a short period of time. So the continuation of the progress is more reliably achieved once this is running the round robin scheduler. So this is a SJF, and here the average response time is a 5. Why? It's a responsive time. Sorry, this is the average. Sorry, responsive time is 0 because as soon as it gets started, it gets scheduled. But for the B, it is 5 for B to get executed. So a responsive time for B is a 5. What about the C? It takes a 10 time for it to be first executed, right? First to be scheduled. So the responsive time for C is a 10. So in average, it's a 5, right? But what if we just take a round robin with the time slice of a one time unit? I'm not sure if this is a second or minute or something. Anyway, I just call it as a one time unit. Then what? A is a 0, B is a 1, and C is a 2. So response time, average response time is what? 1. So it's much better. Great. So yeah, 그렇겠죠? Yeah, this is a trivial, right? But what about a turnaround time for round robin scheduler? In terms of the turnaround time, so round robin schedule, if there are n processes, then the speed of each process will be n times slower, become n times slower. 그렇죠? So in terms of the turnaround time, it doesn't utilize anything about the length of the process, so it's not really good. I mean, I'm not quite sure about this, but it'll be as good as it'll not better than the people in terms of the turnaround time. Yeah, 그럴 거예요, 거의. But it depends on how the length of the job. But it doesn't really, the aim here is not to be optimized, provide a better turnaround time. But this is this is a good strategy when the response time is really the first priority. Okay, and so we learned very basic first people, and then we learned about a priority scheduler, and as an instance of it, we check the shortest time first scheduler and round robin scheduler, which is a kind of a fair share scheduler. round robin 같은 거 fair share라 그래요, because it's the one of a virtue that it try to achieve is a fairness among the different processes, so that no single process become isolated. So it try to achieve different goals. So we learned these three basic steps, and there are more advanced ones based on these three strategies. People, priority scheduler, round robin. What do you think? Obviously, in real world, we use one that mix these three. 이걸 섞어 쓰죠, 당연히. So, but before we moving on to really check the complicated, complex criteria, scheduling criteria, we first check some basic idea behind them, and we try to move on to check more realistic scheduling algorithm. And before moving on that discussion, another concept we need to learn is the characteristic of a process. Some process, so here a process execution, or sometimes this is simply called as a process. People believe that, or people have, it is observed that a process execution consists of a cycle of a CPU execution and IO waits. Why? Because our program is, we write the program as so. First, it receives some inputs and do some computation and generate some output. And receiving input and generating output parts involve IO operation, which need to operate with the IO devices so that the computation will be blocked or it goes to the waiting state for a while. But in the middle, it actually executes some computation. And overall process repeat this cycle many times. For example, for Excel, Excel, first you open up the Excel files, many reading happens, many IO happens, and then what? You write on it. So shortly, it makes some short IO with the user. But if a user gives some command and it do make some computation, and user make a command computation for a while, and at the end, it store all the data back to the disk. So that's very typical scenario of a process execution. And people characterize, we want, the system want to understand, it'll be good for system to make accurate prediction of a process's behavior. Why? Because once we understand it, we can find a better chance of an optimization. So people have a conceptualized this pattern of the process execution and coin a concept CPU burst and IO burst cycle. When it means CPU burst means that this is the period of a process that intensively uses a CPU and where IO infrequently happen. So when a process falls into a CPU burst, it just use a CPU for a pretty long period of time. We call that as a CPU burst time. But sometimes period of its life cycle, process sometimes goes to the IO burst phase. In this phase, it frequently invoke IO and infrequently use. In relatively short term, it use CPUs. So, and there is some CPU burst phase and IO burst phase repeatedly occur over the program execution time. So this is a kind of a profile of a process execution. And here you see that burst duration. And when it means a burst, then it, without a context, then it means a CPU burst. When it says a burst, it means a CPU. Because we don't really have an IO burst. IO is dedicated to the different devices. So we have a more I/O frequent phase, but we hardly say I/O burst, but we use a CPU burst. So this is a period of time. So it uses a CPU. So this is a what? This is the length of a CPU burst. So think about here. We have we execute the instruction without I/O, and this period, this phase is called as a CPU burst, and we can measure the length. We can measure the length what between two I/O we can measure the CPU burst length by measuring the time between two I/O operations. I/O operation 두 개 사이 시간 재면 되겠죠? And then it goes to the I/O phase, and then it goes to the CPU burst phase, and then I/O, and here I can have another CPU burst and I/O. They are repeated. And what if we measure this length, CPU burst length, and make a kind of a histogram of it? Then here will be the CPU burst length, and this is a frequency. And this profile shows that, I do not know about this program, but this program have a kind of a logic that frequently contains CPU for like a 3 milliseconds, I guess. Usually, once you start to use a CPU, then it is very likely that after 3 milliseconds, it try to invoke some I/O operation. We can make such prediction, right? Then what? If system is aware of this information, then scheduler can predict that, okay, how much time should be given to this process before making an I/O. Different programs have a different type of this, different characteristic as they have a different profiles. Okay, so this is a, so we will use this term CPU burst in later discussion. So here define it. Have any question here? Or so far, all right? Okay, good. Okay. And incorporating I/O. So here, scheduler make a decision, scheduling decision when I/O gets completed. And the blocked process get back to the ready queue. Yes, this is another job of the scheduler. Scheduler not only make a preemption decision. Preemption decision means that whether to kick off the currently running process to the back to the ready queue, but also another job of the scheduler means that when an I/O is completed, then it bring a waiting process back to the ready queue. That is another action of the scheduler to make. Okay, and then what? It'll be better for schedule the one with the shorter CPU burst first, and then schedule the longer CPU burst. Why? If we make it so, then the I/O time for this job, I call this as A, I/O over A can be overlapped with the CPU burst of a B. So here's the story. So here we have A and B. A have a relatively short CPU burst time, whereas B is more like a CPU intensive process. So it really I/O happen in B, but B have a very long CPU burst period. So if we simply execute the A first, then A use a CPU, and then it try to use a disk. In meantime, the CPU is simply sitting idle and cannot be used. And when all the job for the A's are done, then B's are scheduled. So here, the sum of the turnaround time is 140. But if we first execute A, and when it goes to the I/O and does not need to hold the CPU for a while, then what? Overlap the B execution so that B make a progress by using the CPU. So execute the B. Then if A can get back by complete as the I/O is done from the disk devices, then A take over the CPU, and then when A go back to the I/O, then B take over the CPU again, so that their execution can be overlapped. In such arrangement, we can achieve a total turnaround time as 100, so that it provides better performance in overall. This is a kind of a basic idea that the time sharing actually improve the performance. 예. 사실 타임 쉐어링만 한다고 하면 퍼포먼스 자체를 높이지 못해요. 타임 쉐어링을 한다고 하면은 그건 그냥 time sharing is only for simply time sharing if it is just used without this type of CPU overlap, then time sharing does not improve performance. But by using the time sharing together with the in consideration of the I/O operation, we can overlap the I/O time and CPU time so that whole execution time can be reduced. This is another important principle that scheduler algorithm utilize. Okay, and before moving on to the next discussion, in order to understand why this incorporation of the IOs are merely desirable thing, let me re-emphasize. I think many of you already learned this from the computer architecture course, but let me remark that IO operation is really, really slow. So let's see. So this is a kind of a table that compares CPU time, CPU cycle time. CPU cycle time means the time for CPU to execute one instruction with the other operation of a computer, including I/O operation. So one CPU cycle is a 0.3 nanosecond. But as a human being, nanosecond doesn't really come to us really directly, right? So people just scale this up so that why don't we just say one CPU cycle is taking 1 second and rescale the all other times as well. CPU 1 cycle 걸려요. And then what? Level 1 cache takes 3 seconds. Reasonable. Level 3 cache, 43 seconds. So one access of the memory from the, and that access doesn't really go out from the CPU, but it was treated inside of the CPU, but by L3 cache, it only take 43 seconds. But if we really touch on the main memory, then it takes 6 minutes. Order of magnitude, it is slow. And if it touches SSD devices, it takes 6 days. CPU has that much time available for a single operation of a device access. And if you're touching a hard disk driver, it takes several months. And if you're accessing some internet, it's several years. CPU is that much speedy. So always it is important. It is always good if we can give some job to the CPU when I/O happens. 무슨 말인지 알겠죠? So this is the motivation of trying to making overlap as much as we can. The scheduler is operating. Okay. So I think this is it for the chapter number 7, and I'm moving on to chapter number 8. Let me turn on the next slideshow. Okay, so based on the primitive scheduling idea, let's first check more realistic version of the scheduler called multi-level feedback queue. Multi-level feedback queue. Here, 2 words are important: multi-level and feedback, and queue. So multi-level here means that this scheduler maintains multiple queues, not a single queue, but it maintains multiple queues. And each queue have a different priority. So you have a multiple queue. And if there are several, so different processes are placed on different queue. And suppose the priority is arranged in this manner, and which one should be first scheduled? The one have a highest priority. So it kind of it leverages the idea of the priority scheduling in order to provide better time performance, better turnaround time performance. Okay, in that sense, this is a multi-level, but it's kind of a queue in a sense that process reside in the same queue. Their scheduling is governed by pretty much the same manner as round robin does. pretty much the same manner as round robin. So there are class of the processes, but within the same class, they have an equal chance for the scheduling. So in that sense, this is a round robin. For what? To provide better responsiveness. So both performance and responsiveness is achieving both of them at the same time is the goal of the multi-level feedback queue, which is our desire when we operate the system. Because we open up some web browser or PowerPointer, Office suite kind of program that involve human interaction. We want them to be reliably offer high responsiveness. That's our desire. But in meanwhile, in background, we run Dropbox, we run networking stacks, and we also run Kakao kind of stuffs that periodically runs and then try to provide some service for us. Maybe you put another process in behind that do heavy computation, which doesn't really happen in our computer in laptop, but sometimes we need to run very long computation. For example, sometimes we run like a backup kind of stuff. Backup doesn't really take a lot of time, but I think more suitable form is why don't we think about converting some video from a format to a different format, which I frequently do for uploading my video lecture to the YouTube. It takes a decent amount of time. It involves a lot of computation. So I just launched that, and I want it to be completed in a few hours. All those jobs are sitting in my same computer. Then what? I want interactive program to be responsive. And then also, I want my long-running program to make a continuous progress on it. And whole system will be nicely managed. So we do, as a user, have a multi-objective. So it is very natural that realistic scheduler also target to achieve different objectives at the same time. But the question is that how to coordinate them, how to make a nice orchestration on different purpose and for different aims of a system. Okay, so classify the processes into multi-level with respect to their interactiveness. So higher priority, interactive process needs to get a higher priority so that they can be frequently scheduled. Okay. And so that it means run priority scheduling for the processes across different levels. The higher level have a higher priority, but meanwhile, run the fair scheduling, round robin type of stuff for processes of the same level. Yeah, so you try to target both matrix at the same time. And we kind of have this idea in real world. 근데 이런 스케줄링 같은 거에 사실 여러분 컴퓨터 사이언스 있기 전에 있었죠. 어디서 있었겠어요? This kind of a scheduling idea does exist even before the computer appears. From where? Operational research. You ever think about you managing the factory, or you are running some business, and you need to manage the human resources and also machines to make some product. At there, we basically have the same problem, and these strategies were exactly found in those areas. 실제로 그 산업공학 우리 학교에는 이제 하는 분이 있었죠. 근데 지금 다 학교를 떠나셨는데 김우성 교수님이랑 옛날에 김상환 교수님이랑 분들 산업공학 하셨고, 저기 신성윤 교수님도 학위를 산업공학 하셨고 한데, 거기 오퍼레이셔널 리서치 OR 하시는 분들 때문에 OR 하는데 거의 그대로 나와요. 거의 그대로 나와요. 여러분이 실제로 경영 매니지먼트 쪽 가서 수업 듣다가 보면은 저기 이렇게 하다 보면은 갑자기 어느 순간 수학이 많이 나오는 지점이 있거든요. 거기에 뭐 큐잉 티오리 배우고 뭐 이러다가 보면 이거 그대로 나와요. 이거 그대로 나와요. 똑같아요. 왜냐면은 여기서 뭐 그렇게 컴퓨터 스페시픽한 내용이 별로 없어요. 이건 그냥 일상생활에도 있는데, here's one real world example is this one. Once you check the cash line in a big market, there are different cash lines. There we have a queue, right? And I found this from nearby supermarkets. I frequently found it, but do you know the special line for small payment? So what do you call that? For small baskets. there are special lane for the small basket. And 그 소액 전용 이렇게 있죠. Only for they're here. They usually have some priority lane for the small amount of the purchasement. Well, why? Because they quickly send out the customer out to from the market, so that they provide a higher priority if they have a short job. I mean, a small amount of the job, so to mitigate the overall workload in the casual lane. Good job. Yeah, the same here. But the thing should be treated with the priority needs to be shorter one. 그렇죠. 짧은 거면 빨리 해도 돼요. 예. But also, even though they have a higher priority, what if there are many short jobs are there? So all of them, majority of the processes are trying to achieve, try to exploit the priority scheduling. Then overall performance of the system will be later hurt by that. So we need to manage the amount of the job that have a privileged execution priority to improve the overall performance of the system. So those needs to be carefully managed. The same thing here. Yeah. Okay. But here the question is that, so this can be possible. This seems good if it is possible, but it is not natural to make it possible, because in order to make this decision, we need to predict what? CPU burst time. I mean, shorter job, which means that the one that have a short CPU burst time should have a higher priority. Okay, if we made it so, we here agree that the performance will be better in system-wise. But how can we predict the CPU burst time and assign priority to them according to it? 이걸 어떻게 할 거냐는 거예요. 관상을 볼 겁니까? 관상을 딱 봐가지고 얘는 빨리 죽을 상인가 봐가지고 빨리 죽을 상이면 빨리 스케줄 해주고, 뭐 얘한테 CPU 주고 나면 좀 금방 해올 건가 이렇게 할까요? It's really non-trivial, but it'll be hard to achieve a perfect prediction, but we can achieve a pretty nice prediction once we use some historical data on the process. So the basic idea is that we first assume that all processes that are newly created have a short CPU burst time. So they just give a chance for using the CPU. And then after that, we measure how frequently. So what's the tendency of the CPU burst time for each process? And if we take a longer process CPU burst time, then the system degrades its priority. And if we quickly return the CPU once it gets, then system recognize that as a kind of an interactive process, so to keep it in a higher priority. That makes sense, right? 그렇죠. 예를 들어서 은행에서 돈을 빌려줘요. 은행에서도 돈 빌려주고 빨리 갚으면 좋아. 이 사람이 빨리 갚을지 늦게 갚을지를 몰라. 그럼 어떻게 하면 돼요? 일단은 신용을 다 높게 해준단 말이에요. 그래서 다 일단 최고 신용으로 빌려주고, 빨리 돌려주면 그 신용 유지해주고, 빨리 안 돌려주면 어떻게 해요? 그 신용 떨어져요. 똑같은 논리. Okay, so let's check one. So these ideas run behind MLFQ, multi-level feedback queue. Feedback means this one, user history. We record the CPU, we determine the likely CPU burst time by what? Based on the feedback. Feedback means the recent record of each process. And using them as a feedback, we can determine the CPU burst time and utilize them to implement nice pseudo priority queue. That's the MLFQ approach. So let's check some more details of the MLFQ mechanism. So first aspect of MLFQ is, as I said before, it runs a multiple ready queue, not a single one. So for example, like this, from the lower level priority queue to the high priority queue. And each queue holds a different number of ready processes. All of them are ready processes, by the way. 그렇죠? ready queue는 항상 ready processes 있습니다. And then scheduling algorithm. So we will develop the scheduling algorithm incremental manner. So let's check very first naive idea of the scheduling algorithm. So scheduling algorithm is merely a logic that determine which process to execute in next turn. 그렇죠? So it can be written as a procedural logic, but also it can be expressed as a more like a rule kind of stuff. 룰로도 쓸 수 있겠죠. 그래서 the first rule means schedule from the non-empty queue of the highest priority. So it check from the very highest, the highest priority and down to the lower priority and check whether queue is empty or not. And if it meets some non-empty queue, then it make a decision that, okay, from this queue, I will pick a one process. But if that process have a multiple process, then what? Round robin. Round robin means basically people. People is a people, but give a time slice. That is round robin. 그러니까 people에서 time slice를 주면은 round robin. 우리가 아까 people, so the genuine algorithm of the people is a first come first serve without a preemption. But we can understand the round robin as a kind of a people, but make a preemption at regular time basis. Okay. So that is a rule number 2. Choose a process from selected queue in a round robin manner. Okay, good so far, right? Then here the remaining question is that then how to decide to which queue a process is given. I mean, to which process, to which queue, or to which in which priority a process should be assigned. Here we don't talk about that yet, but one simple solution is that user or administrator of the system assign the priority. That's true, and it should be done in some way. Then what? Another thing is determined by observed behavior. I mean, previous user history as a feedback to adjust the priority, so the system can automatically find out the proper priority of a process based on a history. So here another job for the scheduler not only so that in MLFQ, scheduler also works for adjusting priority over time. So here the intuition behind observation is that interactive process run for a short period of time and then what? Goes to the block state. And obviously, in order to do so, it relinquish. Relinquish means that it release CPU frequently. Then by observing this behavior, then we can identify this type of the process as an interactive one. It can be characterized by having short period of a CPU burst time and frequent I/O operation. Of course, right? And then what? The opposite. We can identify some CPU as some process as a CPU intensive one when it uses up all the given time budget when it is executed in round robin manner. So if you are running a round robin scheduler, sometimes that context switching happen only for, preemptive scheduling happen only for certain processes. And the other processes are not really have some preemptive scheduling experience. Why? Because even before the time slice or time quantum get expired, process itself voluntarily yield the CPU for I/O operation. Then what? It can recognize that, okay, this one is a really interactive one. Whereas some CPU is, some processes always get preempted by the scheduler, then what? Because it has things on it is more like a CPU intensive process. So it try to maximize the CPU utilization as much as it can, so it hit on the time slice expiration. So by observing these events of a CPU or in execution time, we can capture the strategy is that scheduling algorithm for controlling the process priority. So at the beginning of each process, it is initially placed at the highest priority, which means it is placed on the highest priority queue. And then what? Process gets degraded to a one lower level if it uses up a time slice. Because within a highest priority queue, round robin manner scheduling happens, so that each process will have a one-time slice and it gets executed with the highest priority. And if the process use up the whole time slice, then what? This one is long enough to afford it in a highest priority queue. Then what? So that it moves the one lower level priority queue. But if a process releases the CPU before the time slice expiration, then system recognize that, okay, it can be still afforded with the highest priority queue. So it can be retained so that it stay at the same priority queue. Then what? CPU process start from the highest priority and gradually move down to a lower level and stay at some point in lower level priority queue. Okay. So that process can find their proper position among the different levels of the priority queues. So this is idea. But can anybody point out some limitation of this approach? Anybody? 뭔가 딱 여러분이 프로세스 입장에서 이렇게 하면 억울할 것 같은 생각 안 들어요? 그렇죠. Yes. Some process do some heavy computation at the beginning, but it can move on to more interactive functionality in later phase. But once it have a long CPU burst time, then it will be put to a lower level priority, and there is no chance to make an upgrade of the priority. Upgrading priority. There is no possible way for upgrading priority. So it's not dynamic in that sense. Yeah. Oh, before discussing the limitations, let me show you the example. So this black one means certain process. So it starts from the highest priority queue and its time slice expires. So it moved down to the low level, expires. So it just stay in the lowest priority queue. 이렇게 찾아 내려온 거죠. And here's another picture. So here we have a two process, black one and gray one. So black one goes down and sitting in the lowest priority. And gray one starting from the highest priority, but this one is have a really short CPU burst time, so that it just keeps stay in a CPU. So doing CPU and taking some IO waiting, and in meantime, the lower priority process can be scheduled. And as the gray one get back, gray one override the lower priority process as the shortest shopper scheduling does. So it's a priority scheduling and do very quick CPU computation and go back to the IO. And then, the black one gain the CPU chance again and continue its execution. So their execution can be overlapped. Make sense? This is one of a nice story that can be made by MLFQ. But problem happens. So first, the problem is that what if the non-interactive process can be left out from the scheduling? Or I call this as starvation. Left out from the scheduling if there are too many interactive ones. So check this one. So this one go down. So we can say that this is a non-interactive process. But still, this is a process and right to have a chance for execution. But eventually, this dark gray and light gray processes are coming in, and they are interactive as they use the CPU frequently, but there are many of them. So round robin scheduler keep have some ready item in its queue, then which means that the whole CPU time will be dominated by the highest priority queue. Then the one that's sitting in the lower level priority queue will have some starvation. So this is not an intention of the user, right? So this is one of the problem. Another problem there is, yeah, this is the problem indicated we have discussed earlier. A process have no chance to upgrade its priority, even its behavior will change. Yeah. So in that case, this is not a good job. So people have devised some solution. So first solution is that first the strong way to avoid these two problems is that theoretically, but this period is much larger, far larger than the time slide, but in every S time, this is a pretty long period of time, then what? It just moved the whole process in different queue to the top priority queue. It just elevate the whole process unconditionally to the top and make a readjustment of their priority. So to avoid starvation of the lower process, and also so to mitigate the risk of having interactive process in lowest priority queue, lower priority queue. 뭡니까 이거? 이렇게 되면 어떻게 돼요? 근데 이건 굉장히 뜨문뜨문 일어나겠죠. 자주 일어나면 안 되겠죠. 뜨문뜨문 일어나는데 어떻게 돼요? 매 7초마다 이렇게 양극나프를 부는 겁니다. 부 이렇게 소리가 나는 거예요. 멀리서부터. 그럼 뭐죠? 나니아님이 오시나? 아 저기 아슬란이 오시나? 아슬란이 오시는 거예요. 아슬란이 오신대. 아슬란이 오시는 거. 다 올라갑니다. 다 소리쳤어. 오케이? Another vulnerability is game. So maybe game means that some agent can treat the system by understanding each possible reaction. 이걸 뭐 게이밍이라고 하거든요. 어떻게 하냐면은 maybe a user adversely write a program to make some meaningless I/O in order to keep the process in a high priority. And this is not good. If system just allow this type of thing, then it can be really, it'll be not good at all. So one possible way to avoid this one is that aging. Aging means that, yeah, if a process use up all time element means that it's not only how frequently it is, but it just give a kind of a time budget, overall time budget. And if one process use up all those time budget over multiple chance of execution, then what? It just simply degrades the priority. So you use a lot of time, you use a lot of portion of the CPU, then you just move down, no matter you are interactive one or not. You just move down. But this should be used together with this priority boosting. 이 priority boosting이랑 aging이랑 같이 쓰면은 side effect가 좀 사라져요. So once it is used together with the boosting, this aging is that kind of nice idea. So one that try to dominate CPU for a long time will have a lower priority, so that fairness on overall system overall will be more well managed once we have this aging account. Okay, so yeah, so for example, this gray one, it uses a lot of time in overall, although it is interactive, although it can be say it is interactive, it uses already much time on CPU, then you should be evicted. You should be evicted by lowering its priority. Yeah. This is the idea of aging. This is the final slide. So 이게 재밌는 거 있는데. So, but this is the final slide. So let me tell you about this. MLFQ is a pretty nice idea. It innovates multi-process scheduling at the edge. But one of the limitations of the MLFQ is that it have a different parameter. So for example, what would be the proper time unit for time slice, or not time unit? What would be the proper amount of the time slice or time quantum? What would be the proper amount of time for priority boosting, or what will be the criteria, what will be the proper value for the time allotment for the aging. All those parameters, how can we get that? We have no idea. And it depends largely on the system, and it depends largely on the characteristic of the workload. And it is the administrator needs to find that parameter well. And if it is well tuned, the overall system performance will be good, but we have no real idea for how to find this nice parameter automatically. That is kind of the limitation of MLFQ. So people devise more simple but good scheduling algorithm, and we will cover that in later chapter. But still, this MLFQ idea is widely used in our modern operating